Hello, hello, hello. This is Nicholas. I'm really excited about this video. It's finally getting into the meat of multivariable calculus now that we've got kind of the preliminary stuff out of the way. And this video is going to be on probably the most important topic in multivariable calc, and that's partial derivatives. So you're familiar with the idea from Calc 1 and Calc 2 of just quote, normal derivatives, I guess. In other words, normal derivatives are concerned with single variable functions. That's why it's all called single variable calculus. So, for example, if we have a function, everyone likes to pick on x squared, so let's do that. That's f of x equals x squared. Then you're familiar with the fact that I take the derivative of x squared, I get 2x, and that 2x tells me that if I were to pick any point on this curve and draw a line tangent through that point, its slope would be 2x for the value of x that you choose. So now we extend this idea to functions of more than one variable. So a thing to remember is that, see, this is a function of just one variable. It's f of x, and we'll say it's x squared. In general, single variable functions have the form y equals f of x. So you take in an input x, you get out an input y. So x is your independent variable and y is your dependent variable. And so it takes 2 dimensions to graph a single variable function because there is one axis for your independent variable, your x, and then one axis for your dependent variable, y. And so you need 2 perpendicular axes to graph any single variable function. As an extension, it would make sense that if I have a function z being equal to f of x comma y, it would take 3 dimensions to graph this double variable function. In other words, this function with 2 variables, because here we have 2 independent variables and 1 dependent variable. So we put in an x, we put in a y, and we get out a z. For example, just quick so you know what I'm talking about, if I have z equals, say, cosine of, let me make it like this. If I have f of x, y being equal to x squared plus y squared, and I want to find what f of 1 comma 2 is, well, that's just 1 squared, which is 1, plus 2 squared, which is 4, and so 5. So it works the same way with single variable functions as it does with multivariable functions. You plug in values for all of your independent variables, plural, because now there's more than one, and you get out a single variable for your, or a single number for your dependent variable. And so it would make sense then that since you have 2 independent variables, you need 2 perpendicular axes, but then you also need a third one coming out that's perpendicular to the 2 at the same time. And we call that the z-axis. And so this picture here that I've drawn is in what's called R3. And what that means is 3-dimensional space. So for example, where does this R3 come from? Well, if you're familiar with the fact of R itself, that in set theory means the set of real numbers. And we have this thing which will come up later, and so I'm going to define it now because it will be important later when we get to integrals, called it's called the Cartesian cross product. I'll just call it cart cross product. And so the Cartesian cross product basically allows us to, not the cross product with vectors, but it allows us to take a region of our choice and clearly define its boundaries. So for example, if I have 1 and then maybe that's 2, so 1, 2, and then this is 1 and this is 2, along our x and our y axes, and I was concerned with the region here where we've got it bounded like this, then this whole region here, we could, if we called that region D, then D would be written as, we would have 1 comma 2, our x numbers, crossed with 1 comma 2, our y numbers. So you can think of R3 actually as just the Cartesian cross product of three number lines perpendicular to one another. In other words, R3 is R cross R cross R, because the number line, or in other words, the x-axis crossed with a number line in the y-axis creates a plane, the xy plane. But then what you can do, and I'm going to draw it a little different, if we have an x-plane, a y, and then if we cross that with another, a z, then we get three dimensions here. We have an x, a y, and a z. And so that's where the notation R3, or really Rn, comes from. So now, the whole idea of the partial derivative, the definition of the partial derivative, we define partial, let me draw it good the first time at least. It looks like a partial f with respect to x. It's not a 2, but it's called a partial. Partial f with respect to x. We define that to be the limit, obviously, if it's a derivative as h goes to 0, of f of x plus h comma y. This is for two variable here. It can be easily extended to n variables, minus f of x y over h. And likewise, we could define the partial of f with respect to y to be the limit as h goes to 0 of f of x comma y plus h minus f of x comma y over h. And another way you might see these written is f with a little subscript of x and f with a little subscript of y. Just another way of writing it. And so what is this partial derivative telling you? Well, it's telling you, see, the idea is that we have to hold all of our variables constant, all of our directions of change, except for one, and then let that specific variable change. So in this picture here, we have this purple surface. So it's a purple surface in the form z equals f of xy, and it's actually what's known as a paraboloid. Paraboloid, I think paraboloid. Why? Because if I were to take cross sections like how I've done here, you can see that this right along here forms a parabola. That's not so much my point, but I just wanted to point that out. So now what we do is, so let's say this, I know the picture's a little blurry, but so this here is the x-axis, and then this here is the y-axis, and then going up and orthogonal to the both of them is the z-axis. So we have two independent variables. We have to let all of them be fixed at some constant except for one of them. In this case, there's only two, so we just pick one to be constant and we let one vary. So the idea is, they said, well, okay, I'm going to take cross sections along the y-axis. You can see that that's what they've done here, because this cross section here is along the y-axis, right? It looks like at about y equals 1 right there. And so x is held as a constant. And so now what we get is this two-dimensional cross section. Since the surface is in 3 dimensions, we get this plane cut at it. And so now what this tells us is that now we can measure change in a specific direction. And that's what the whole partial derivative idea is concerned about. We have to let every variable except for one remain fixed, because if we didn't, then there would be infinitely many directions we could go, right? We could, in other words, we wouldn't be able to measure change, because there'd be all sorts of different directions we could go, right? We could take maybe a cross section like along here or something, or along there or something. And so in other words, there would be infinitely many different rates of change. And so we say, well, all right, we're going to keep everything constant except for one variable, and we're going to let it vary. And when we do that, we create a curve that is just in some plane, that is just contained in some plane, because it's a cross section. Or later, when we generalize to more variables, it'll be called a level surface. That's just a fancy word for a cross section, but the function has more than two independent variables. So as an example, let's consider f of xy being equal to, well, I think I did x squared plus y squared before. So if we were to find partial f with respect to x, we would just get 2x, because here x is the variable, y is treated as a constant, because we need to keep y as a constant in order to measure any sort of meaningful change. And so the derivative of a constant is 0. And then likewise, partial f with respect to y is 2y, since y is a variable and x is a constant, and the derivative of x squared, which is a constant, is 0. And so what does this mean? Well, it means that if I were to consider cross sections along, let's first consider along the y-axis, since that's what I have here. And by the way, this x squared plus y squared is actually the graph. That's what this graph is here. That's why I picked it. So partial f with respect to y turns out to be 2y. What does that 2y tell us? It tells us that if I were to take cross sections of this graph along the y-axis, I would get these 2D graphs, and these 2D graphs, I could then consider what those would look like and what tangents to those points along that 2D graph, what their slope might be. And so what the 2y tells us is that if I were to take a cross-section perpendicular or along the y-axis and then slice perpendicular to it, then I get this two-dimensional parabola. And so if I were to pick any point y along the parabola, and it's y that we're considering because x is held as a constant, and then z's are a dependent variable. So if I pick any value for y, what that tells me is that the slope of that blue line right here, this tangent line, at that point y is 2y. And so likewise, if I were to, I'm not going to draw it, but because I'm not good at drawing, but likewise, this partial f with respect to x equals 2x tells us that if I were to take this gray cross section here and I were to instead do cross sections perpendicular to this gray plane, so in other words, I can see if I can try to draw it, it would be kind of going through like that. That's bad. Let me try again. So along the x-axis basically is my point. Then what we then get are these curves along here. And so if I were to take a tangent to those curves from that cross section, then what it tells me is that if I pick a particular value of x, and I'm not picking a y because x is varying and y is held constant, then the slope of the line tangent to that curve on the cross section of the original function is given by just the 2x. So it's a similar idea to normal derivatives. Basically the crux of the partial derivative is that we need to keep, I probably should write it out in words, we need to keep all independent variables. So in this case, we just have two independent variables, an x and a y. But the idea is we keep all, if we had a function of n variables, we keep all independent variables constant except for one. And then from there, we can take cross sections along that axis. And then what we'll get is just a function of the variable that is of the only variable that isn't held constant. So I'll write it as f of not constant. So not constant, which is a two-dimensional function. So in other words, it lives in R2. It lives in two-dimensional space. And so when we get that cross section, what we can do is say that the partial of f with respect to the not constant variable gives the slope of line tangent to the tangent to this f here that is living in two dimensions, and it gives that line tangent to f on that cross section. So I hope the picture now actually makes sense to you, and I hope that the idea of the partial derivative is pretty intuitive. Maybe one more example. Let's consider f of xy being equal to, I don't know, x cosine of y. And so let's find partial with respect to x. Well, that's going to just be cosine of y, because x is the variable here, y is a constant, and so therefore cosine of y is a constant as well. So we can just treat cosine of y as just a number, like 1, okay? When we take the derivative of 1 times x, we just get the constant, or just 1. And so that means the partial of f with respect to x is just cosine of y. If it were x squared times cosine of y, then we would get 2x cosine of y. It's the same idea, just treating y as the variable or y as the constant and x as the variable. In the partial of f with respect to y, now we're treating y as the variable and x as the constant. So in the original example, where it was just x cosine y, our derivative with respect, our partial derivative with respect to y would be a negative x sine y, because our x is just a constant, so it stays there, and then we take the derivative of cosine y, which is negative sine y. If this were, say, x cosine squared y, then what we would have is we'd have negative 2x cosine of y times sine of y. So I keep x where it was, and then I take the derivative of cosine squared y, and the derivative of cosine squared y, we do the power rule, we get 2 cosine of y, times the derivative of cosine of y, which is a negative sine of y. And that's how I got that answer there. So I hope this idea of the partial derivative makes sense to you. And just to say it concisely, the partial derivative measures change along specific cross sections of the one particular variable you are not keeping constant, and it tells you the slope of lines tangent along that cross section. I think with that, we're done.